All right. So here's today's lesson plan. So I know I usually start with the quizzes, but what I'll do is I'd like to run you through what a truss is first, as well as what a zero force member is. And yeah, as usual, um, feel free to ask questions, and I'll try my best to check the chat as questions pop up and like periodically. Okay, so yeah, in today's lecture, you learned about trusses. But first, before I explain what a truss is specifically, I just want to have like the more like overviewing um, kind of perspective in terms of where it sits relative to other things that you've been learning. So essentially, we're stepping into the territory in statics of analyzing structures, right? So there's two basic types of structures which you'll learn in this course. There's frames and there's trusses as well. So for frames, so that's what we've been kind of dealing with maybe, um, well, we've been dealing with beams, which we dealt with a little bit last workshop. And beams are a part of frames. So it kind of looks like this. Oh, sorry, I'm in an unusual setup today. Um, so excuse me if my handwriting's not great. So actually how it works is frames fall under beams and columns. So beams will be your horizontal members, and columns are vertical members. And I'll draw a little diagram of what they look like. Yeah. Oops. So a frame kind of looks like this, where it's well, it could be pinned or rigidly connected to the ground. But I guess the distinguishing feature here is these are rigid connections at the corners. I'll explain the different types of connections shortly after, like just underneath this section. But these are rigidly connected. In short, that just means that if they're at 90 degrees from each other, these two members, the beam and column, they're going to stay at 90 degrees as this whole structure deflects and as we add loading to it. And yeah, just to be clear, we're talking about this being the beam, the horizontal member, and these are columns, right? All right. In contrast to this, right, trusses, they kind of look like this. So I'll do a drawing first. So back when I did this course, right, 1300, I guess like I didn't really understand what made a truss. I just thought it was like a bunch of triangles. Whenever there's a bunch of triangles, it'd be a truss. And yeah, but there's a few things that make it stand out. But the main thing I would say is that these are all pin connections at every joint, right? At every joint. Cool. Yeah, if you have any questions about that right now, just ask away in the chat. I'll be, yeah, periodically checking the chat as well. Okay, cool. Yep, so those are our basic structures. I also want to note that every now and then you might hear the word machine. So machine is kind of like a mechatronic or mechanical kind of concept. Um, but they're solved very similarly to frames. So like mathematically, I would say they're pretty similar to frames, but but I guess what distinguishes them is two things. The first is the scale of things. So as I mentioned last time, frames will be in the kilonewtons and meters kind of scale, so pretty big, whereas machines are in newtons and meters. And machines can also have some weird stuff happening to them, like for example, springs can come off of machines, whereas you don't normally see springs in a frame. And I would say, yeah, the majority of frames are shaped kind of like this at 90 degrees from each other, because if you imagine a building in real life, right, you kind of want it to be built like that and not really, like a machine might look like this, for example, this shape. That just doesn't really make any sense for a building, right? So yeah, cool. All right, I'm gonna move on. Next, we want to talk about connections. So there's actually three types, and the three types, there's kind of a, what do you call it, equivalent to supports. So we've learned about the supports last time. So just to recap quickly, there's a roller support, you have your pin support, and you have your fixed support, right? Um, and they kind of had your normal force reaction for all of them, tangential for pinned and fixed, and the fixed support also had a moment reaction, right? Counterclockwise, positive convention. Um, so essentially, the equivalents here are roller connections, pin connections, and rigid connections, right? And so here's what they might look like. Actually, I'll start with the pin connection. Sometimes it's called the simple connection because they're fairly common. Like in trusses, like, yeah, here's your pin connection. So that's your truss. Yeah, so that's like a pin connection, right? Your rigid connection, as I said before, a frame is a good example of that. Let's get rigid connection there. So a roller connection, I've only ever seen this in machines, so not really in structures, essentially, right? It looks something like this. I didn't want to draw this badly, so I just copy pasted this from a question I found. Yeah, so this right here is the roller connection. I'm going to zoom in a little bit, talk about it. So it's essentially like this little knob that sits within a slider of this machine, and it resists the normal forces. Sorry, it's free to slide this way, so this is the tangent. This is the tangential direction, and then the normal direction is this way, right? So there'd be some normal reaction like that. Okay, cool. Yep, and last thing I want to mention with connections is they're between members, and so when we're talking about, for example, here's a roller connection, right? Sorry, here's a roller support, right? The ground is essentially something that we assume doesn't move in our free body diagram or in our system, right? So you have your member kind of interacting with the ground, which is something that doesn't move, right? The difference with a member is that here's a member and here's a member, right? But these are both subject to move. And so when you have two members being connected, that's what we call a connection at the joint there. And so yeah, anyway, that's what a connection is. I'm going to check chat as well to see if we have any questions to do with that. We're good, it seems. Cool. Yep, and then I also want to talk about simply supported beams. So I talked about this last workshop. But yeah, we have our pin connection and a roller. These two can be swapped around and it would still be a simply supported beam. So if this was a roller and the other one was pinned, right? And what makes it simply supported, right? We have three unknowns, which are our reactions. And then we have three equations of equilibrium to solve it. And therefore, it's going to be statically determinate. Right? Which is good, which just means we can solve it. And here is another word which might come up, particularly in the next lesson, cantilever beam. So a cantilever beam, right? I'll do it in purple. So before we had these reactions. Um, this also has three unknowns, right? Let's call it MA, AY, and AX, right? So it also has three unknowns, and this is a free end here, so it's not connected to anything. Right? And so it's the exact same thing as simply supported beam, but it obviously has different properties. But yeah, it's just another common structure because it's, I guess, as simple as it can get without becoming unstable, right? So the idea of instability, as before, is like if we change this pinned end to a roller, right? Now we only have two unknowns, but once we apply an external force, say like diagonally, well, now it's going to start moving, right? Which kind of defeats the purpose of a structure, right? So that means it's unstable. Anyway, but that's not the case with our simply supported beam and cantilever. Yeah, so those just have specific nicknames because they come up so much, but those are essentially structures that you'll see next lesson a lot. Okay, cool. Sorry, that was a lot, but now we're actually onto trusses. Um, and I'll just run you through trusses and zero force trusses first before I get you guys to do the quizzes because I guess it's important to know this stuff before I can test you on it, I guess. So I'll teach it first. Um, so the first assumption is the one we just talked about, right? All the joints are pinned. That's kind of the assumption we need to make in order for our truss methods to work, the ones which are coming up. The second assumption is that you only have point loading. So no distributed loads are allowed. Like, you can't have W. This no longer is a truss, right? Um, yep. And then they can only happen at joints as well, right? So you can't have this. If you ever see a question like that, that's a truss, it's not solvable, right? So yeah, that's our point loads, and they can happen at any of the points. They can happen at any of the joints rather. They can even happen off of the joints which are supported, right? Those are our two assumptions, and let me just check my notes. I'll just sign in Google. Sorry about this, guys. Give me a sec. The reception's not very good out here. I hope there's nothing wrong with the recording. So I've got a question here. Regarding the example you gave about unstable structures, if you replace both ground joints with pin joints, since there's no torsion resistance, does that make the structure unstable? Okay, that's a good question. It's structured unstable only when there's isn't resistance. Oh, okay. Um, Correct me if I misunderstand your question here, but so if you say that this is um, pinned as well, right? And we have our reactions like this, set up like this. It's actually no longer statically determinate, right? But it's not unstable either. What happens is you actually have too many unknowns. So let's change this up to 4, right? And it's only unsolvable depending on your external loading, okay? So if we only have, let's say we have a distributed load that goes down. Okay, I'm going to start doing the lazy way. It's easier to draw. Oh my days. So that's a uniformly distributed load, right? That's all pointing down, all right? Sorry, it's kind of a lazy way of doing it. And we also have a point load, okay? But everything's only acting down, right? So when we take the sum of the forces in the x direction, um, all we know is that ax is equal to negative bx, right? But because there's no external loading horizontally, we can, safely say that these are both equal to zero, right? As soon as we introduce a diagonal force, something like this, right? All of a sudden, all we know is that ax is equal to negative bx, right? Um, that, this reaction and this reaction are just opposites of each other. Oh, sorry, my bad. That's not complete. Sorry, what we know is this minus p cos theta. It's theta there. So essentially, you don't know what portion of these horizontal reactions are going to AX and which are going to BX, because the only points you can take a moment about are, you know, either on the line of action or somewhere off the line of action, and either you can have, yeah, you're gonna have problem solving it. That's sorry, I'm just talking too much, but essentially you're gonna have problem solving it. So therefore, this is all to say that this is now statically indeterminate, right? Because you have too many unknowns and you don't know which portion of this load goes into each horizontal reaction, right? So it's actually the opposite of the unstable case. We kind of have it like this, right? So unstable is when you have too few um, reactions, yeah? And then statically indeterminate is when you have too many. Statically determinate is what we can solve, right? Yeah, cool. I'm gonna check the chat again. Yeah, cool. Sorry, I just spoke for an extra 5 minutes longer than I needed to about that. But yeah. So back to trusses, yeah. Um, I've got my notes up now. They've loaded. Yeah. So effectively, the most important thing to note about trusses, and due to these assumptions, is that all the members in a truss are axial, right? Therefore, they can be in tension or compression. And yeah, from now on, we're just going to assume tension conventionally is positive and compression is negative for our method of joints specifically, right? But this is a good way to remember it, right? Um, and yeah, so that just means that this load here is going to go into this diagonal member, and we're only going to consider the compression or whatever for that. We're not going to consider any shear, so if we have a point load there, it's going to create shear force, which we don't want. Yep, check the chat again. Okay. Um, okay, one last bit. I'm going to talk about zero force truss members, and then we'll have our quizzes. But some of the quizzes questions will involve what I'm about to tell you right now. So zero force members is when you have a truss and you can immediately tell that some of the members will not be taking any tension or compression, and so you don't need to do the calculations for them. It's something like it's a shortcut, and it can speed things up. Um, yeah. So there's two cases. The first one is this one, and you have two members meeting at a point, right? without any external loads. So what I mean by that is if we have an external load happening at this joint, right, we're not going to consider that joint for testing for zero force members, right? The other thing is if there's a reaction happening here, um, then it's not a zero force member as well. We know that. Yeah, so this is just some random joint without any loading on it. And if that happens, then both of them are zero force. Which is 0 kilonewtons, right? Um, the second case, sorry, let me just keep it there. The second case is when you have three members meeting without any external loading. So same thing goes as before, so no supports here and no point loads here, except specifically two of them have to be collinear, right? So what do I mean by collinear? I'll use the highlighter tool here. Collinear means they have the same line of action, right? So those two are collinear. This member here is non-collinear, right? And if this is the case, then specifically the non-collinear one is zero force, okay? Zero. Yeah. Okay, so those are the two cases where this happens. And I'll show you an example. And this is pretty cool. This is like a party trick, except if you show this to people at parties, probably won't get invited to too many parties. So we have an 11-member truss here on the left, okay? And you have a point load that's pulling down on that joint on the right, okay? And we want to scan this for zero force members, right? So I'm going to go left to right, for example, and just tell you which ones I think are potentially zero force members. So we have to go joint by joint analysis. So this one, it has a support, so none of those ones can be zero force. That has a support, so that can be zero force. Let's look at that one. There's four members coming off of it. So remember, both of our cases, you know, four member ones like don't have a case where any of them can be zero force. Same goes for all of these as we go through. And then once we reach this one here, you'll see that three members coming off this joint, and two of them are collinear, and there's no external forces. So therefore, we can delete that. Maybe I won't delete it for now. Maybe we'll just strike it out. Okay. We can strike out that member. And now, we can be like, okay, cool, now we can solve our problem. But you're going to waste a lot of time because you're going to find that you have to do another pass actually. So if I scan through and do my passes, I'm going to find that I analyze this one and, well, this member's gone now. So now, when we analyze this joint, this one's the non-collinear one with no external forces. So we can actually delete that as well. And same goes when we go through all of these members in this truss, and we're just left with, a truss that's only three members long, right? And so it's going to be much, much quicker to solve. Yeah, that's a pretty extreme case, and I really doubt there's any professor in the world who's mean enough to, give a student that question in a midterm or something, because it purely relies off the fact that you can recognize the trick with zero force members, but it will speed it up considerably, if you do know the trick, right? But yeah, so you know what? I'll run through that part later. How to solve trusses. What I want to show you guys right now is quizzes. Actually, before I show you quizzes, right? I just want to talk about trusses just a little bit longer. So in real life, right? Do these assumptions hold true? That's something you can think about because they seem like very specific, right? But the good news is like engineers can kind of design bridges and they can kind of design a lot of buildings they want to be trusses in such a way that there is only like point loading at the joints, right? So I'll show you. Here I've got the lecture slides. I was looking at this earlier. Let me try to find it. Should be like a 3D kind of picture of a bridge. I can't find it. It's at the top. Oh, I think it's here. Yeah. So yeah. So here we have a bridge, right? And it has this truss. It's like a truss bridge, I guess. And the loading kind of acts top down. So you have your car and vehicles and stuff acting on the road. The road's weight can only be transferred to the sides of the road, right? Um, and then they can be transferred to these, what do you call it? Cross beams, they call it. You know, the cross beams then go onto the truss members at the joints only. And then all of a sudden we have our assumption being met. And so yeah, it's pretty clever. Like, even though it seems like a very weird assumption to make, engineers can kind of design things to work around their assumptions, make things easier to solve. And they've been doing that for like hundreds of years or whatever. Anyway, um, oh, here we go. Got some questions. Uh, when you say external load, does the load have to be applied to the joint connecting to the members in question? Yes. They can't be in the middle of a member. Then it's no longer a truss. How is attendance marked? So I'll have a Google form. I'll show pretty soon after we do the quizzes. It's like a QR code. You scan it, and then you can fill out the attendance on the Google form. Yep. Thank you for answering that, by the way, Leonardo. What's the point of adding zero force trusses and structures? Oh, that's a good question. So let me show you. So like this one, for example, right? Here, like I've said I've hidden it. I haven't deleted these members, right? But there's a couple of reasons. One could be like, for example, say there's like a bunch of loading that happens here, and then this member gives out first, right? Say I guess, you know, uh, it bends like that, right? And then this snaps due to tension. Once this snaps, all of a sudden, these aren't zero force members anymore, are they? So they will have their use in cases like that. Um, yeah, and probably for serviceability purposes, but you'll learn that later if you're a civil engineer. If you're a mining engineer, I'm sure there's some other cool stuff you can learn it later in your degree. All right, cool. Yep, no worries. Yep, yeah, yeah. Right now, like I guess, because I'd say most of you are first years, or maybe you're doing this course in your second year. Everything's just like pure physics, pure maths. It doesn't really come together until later years where you'll see like the practical application of things and the design of structures, for example, or whatever you end up doing. Yeah, like it's really cool when it comes together. And um, I'm not that many years in front of you guys in terms of my degree. I'm in fifth year, and yeah, you'll pick up a lot of the skills along the way, and you'll learn pretty quickly how it kind of applies to real life, which I find to be super interesting. Okay, so I'm going to do the quizzes now. All right, yeah, just scan this QR code first. This isn't the attendance, by the way. This is yeah, if you could just scan it, we'll just test your understanding of like zero force members and other stuff like that. Um, yeah, this quiz is kind of recycled from um, my term 2 class last year, but I think they seem to enjoy this. I also just want to mention that in the form, the attendance form, I have like an optional feedback section. And thank you for the people who have given some useful feedback. Um, so one piece of feedback is that I've now included my notes that I'm looking at right now, like the ones on my phone, ahead of time, in the Google Drive. So if you've got that link, then you can look at the notes if I scroll too quickly or whatever. The problem is I've labeled it in big brackets like work in progress because yeah, I don't want to like if I have any things to fix that I spot along the way, like I want to correct those notes, right? And if there's questions in the Q&A, I'll add it before uploading it formally to Moodle. Um, but yeah, the option's there if you wanna have a gaze at it. Yeah. So I'm gonna start the quiz pretty soon. I'll give a few more seconds for people to join. All right, so I might just start the quiz. So loud. How many questions do I have? Oh, 5. Okay. Yeah, I'll just give everyone like maybe another 20 seconds. Some people finished up now. Okay, quickly finish up your answers. I'll just end the quiz. You ready? 3, 2, 1. It's lagging. Very good. Congratulations on first, second, third place. Awesome. Yep. So let's go to the questions. Oh boy. Oh boy. Okay, not looking too bad. I mean, yeah. Generally when I do these, it ramps up over the term. So I'm sorry to the people who are 100% stressed right now, but yeah, cool. Um, yep. So this is a bit of a troll question. I'm not gonna lie, guys. So it might look like joint B here is a zero force member because we have two members coming off of it, but we have external forces, and therefore this can't be a zero force member, and none of the other ones meet the criteria. So, yeah, there's no zero force members here. Next, we have this truss, and there's a lot of trusses. Sorry, there's a lot of joints and a lot of members, so it's actually a lot to look at. Um, excuse me. Um, but effectively, um, out of uh, out of the ones here, joint G is zero force. Actually, you know what? I'll come back to you next lesson on whether joint I is zero force as well, because I'm getting the vibe that it is. Yeah, I think joint I is as well. So sorry to those people who clicked I.
Cool.
Okay. So here's like some questions that aren't to do with trusses, but they're like a bit more theoretical, I guess. So is this beam in tension or compression? So remember, a beam is a horizontal member in a structure, and yeah, so this is kind of a trick because all the external forces are acting downwards, and none are acting along the axis, like for example diagonally. Um, and there's nothing like pushing or pulling at the ends here of the beam, and therefore there's no axial forces. And regardless of what P is, this is going to be the case, right? Okay. Yeah. So this is kind of like based on practice and vibes, pretty much. But it's saying like, does support B or C take more of the load? So which support reaction is bigger, right? And yeah, it's B. Um, and how would you think about this? So if we completely ignored the part of the beam that's AB, right? We call it, I guess, yeah, A to B. So if it's just B to C, right? B and C will be taking equal loads, right? Because it's symmetrical. But because we added this extra bit to B, um, because we have more of the beam going left here, extending past B to point A, and then we have additional loading on that side, well, then we know that it has to be, um, more of the vertical forces has to be put onto B to account for this, right? Um, yeah. So again, that's kind of this is based on vibes. Like I don't like unless you can do the calcs, right? For it, and it'll check out as well for the exact amount, but you can kind of get an idea of it just by looking at it as well. And I guess that's one way to check if your answers and the numbers feel completely off or not. Cool. Yep. Is the weight of the beam considered? Okay, let me just see if there's other. Oh, thank you. That's a drive. Yep. Let's see. Sorry, I'm catching up on questions. Yeah, I can't answer that. Sorry, about the name in the lab document. If you're not seeing it, you might need to email the lecturer. Attendance form. So yeah, we'll do attendance right after I stop talking here. Um, the 5 and the 10 kilonewton have a horizontal component. Beam question from quizzes. Oh, I know what you mean. For the civil school. So, um, okay. Those those arrows there, the diagonal ones, don't denote the direction of the force vector. They're just pointing at the distributed load. So dumb. Um, but like, yeah, I don't know if you've ever noticed in my working out, right? I always do this like squiggly line to to not confuse people. And also I think it just looks cool, to be honest. But like, yeah, I do the squiggly line because then there's no confusion with that. But yeah, that's pretty much where the confusion is, yeah. Is the weight of the beam considered? Okay, so I know in workshop one, or maybe the first question in workshop two, so last workshop, we consider the weight of the beam, right? Um, but unless it specifically says in the question, like the self weight of the beam is 5 kilonewtons per meter um, of length of the beam, you don't consider the weight of the beam, right? Because they don't give it to you. Like you physically cannot calculate it. Um, so yeah, yeah. So self weight. Yeah, that's pretty much. Okay, cool. So we're gonna have a break and come back, and then we have three trust questions to solve. But for now, I'm going to leave the QR code up, and we'll be back in 5 to 10 minutes. If you have any questions, please just drop it in the chat. I'm just gonna quickly grab some water, and I'll be back. Let's get started. All right. So, moving on to the questions. Oh, sorry. We're going to talk about how to solve trusses first, and then we'll move on to the questions. So, I wanted to group this together after the break with the trusses because, yeah, I guess like it'd be hard to remember what I'm saying. Um, yeah, before the break. So, with trusses, right? What we talked about earlier is identifying and removing zero force members. And so I would say that's the first step. One little thing to keep in mind is, um, yeah, I would cross them out instead of deleting them. Like you delete them, you might just forget that they existed, and so you have problems with like if if like in one of the questions they asked like specify um, the force in every member, and then you might just forget to list off member. Let's say like GH or something. This might be called. You might just forget to list it off as zero force if you just straight up delete it. So I would cross it out. It's a good habit. All right, and then the first real step is to find the support reactions using equations of equilibrium. So it's the exact same as what we've been doing last workshop, where you look for, so in a beam, you know, um, you look for the lines of action, and then you could pick a point which eliminates every line of action for unknowns except for one of them. Except here's the catch with a lot of these questions. For a lot of questions, not a lot, for some of these questions, you won't need every reaction. And what I mean by that is how the questions are worded is that they're interested in the axial forces in each of the members, right? They're not interested in what the reactions are usually. And so if you don't need to get the reactions to solve the question, this is a waste of time, right? So it's something to keep an eye out for. Next, we can now choose our method. So the method of joints and method of sections. And there's a lot of caveats with both of them, and I would encourage you to try to practice questions for both of them. I've included some extra practice questions on Moodle, as well as in my Google Drive. Um, yeah, there's 9 questions, I believe, but you don't have to do, I mean, you can do all of them, and maybe like the best thing you can do is chip away at it. But just keep in mind that the midterm on statics will be more than just trusses, right? So you want to spread out your study for all the different topics. So don't get like so um, tunnel visioned onto just that one. But anyway, I'll try to provide some more on Monday once I prepare it and after my trip for I think we're going on to solve beams and shear force diagrams, bending moment diagrams next lesson. Anyway, so for method of joints, the idea is you use this one when you want to find all the members in a truss, but it's a little bit slower. All right, so just keep that in mind. The other one is method of sections, where you want to find certain members, but it's quicker actually, because you just draw like a free body diagram and of like a section, and yeah, you're only interested in say like 1, 2, or 3 members. Yeah, you do your cut, and yeah, you'll be able to solve for them. So there's a lot of nuances to both these methods. So the best thing to do is just dive in and do some questions, so you can see them. So here's question 1, and I've just redrawn it down below. Um, yeah, I guess I just redrew the same thing, but I'm going to draw over this one. So um, let's read the question first. So basically, you want to find the objective of the question, and here it says you want to find each member, right? So that's method of joints, right? I'm going to quickly check for questions in the chat. No, we're good. Cool. Um, yep, so we're going to be using method of joints in this question. Okay, let's have a look at one more thing in this question, right? So the supports, right? The supports are both pinned, right? But do you remember what I was saying earlier about external forces and the fact that all the external forces are acting exactly downwards in this question mean that this is still statically determinate, even though we have technically four reactions here. But yeah, because of how our loading works, we can effectively just not look at these ones, right? Oh, as in, I don't know if that's the best practice. Okay, we know they're both zero, right? That's the first thing. The second thing is, well, there's a lot of truss members, but this is a symmetrical question, right? Everything's symmetrical about it. The loading's symmetrical, the dimensions are symmetrical, and so we actually only need to calculate half of them, essentially, right?
True.
Um, so here I've written symmetry. Hello, spoiler. So here I've written symmetry. AB is equal to DE. So this is AB here. This is DE here, right? Yeah, because they're symmetrical, they're going to equal the same thing. And then, yeah, you saw down below, but zero force member right here at this joint, and G here is zero force. Right. Cool. Um, yeah, so we're just going to dive into the question. So now so we can solve for support reactions. And let's have a think before we solve the support reactions, right? Do we need to solve the support reactions? And in this case, I would say yes, because think about for the method of joints where you're going to start. You always want to think about where you want to start, and usually it's outside in, right? Um, it's kind of like also based on vibes, but here's where I consider outside. Like it wouldn't be one of these inner joints because usually you don't have enough information to start. Um, but I start outside in, and this top one wouldn't make any sense to start at because we have so many members connecting off of it that it's going to be really hard to start at. Like, it's impossible to start at. So we can either start at A or E, essentially, right? And both are symmetrical. So, you know, um, essentially we just need to start at A. Yeah. So you can do the sum of the moments, all that stuff, but I'm going to do a cheeky trick here because of symmetry. Oops. Due to symmetry, AY equals to EY, which is equal to 1 plus 1 plus 1 plus 1 plus 1 divided by 2. Yeah, so that comes from the external loads, right? So basically they're taking all the vertical external loads, um, yeah, and they're both taking the same amount and they're split in two. So they're both equal to 2 kilonewtons each, right? So that's the support reactions. Okay, next, we want to apply the method of joints, so starting joint by joint. As I said, we're going to start at A. Okay, so I'm going to redraw. So basically, I've made a three-body diagram cut here, right? And I'm just going to redraw the joint. And there's all these forces coming off this one point. We're in particle equilibrium, so there's no moments happening, right? So with method of joints, we don't use sum of the moments. Um, yeah, you can't. Well, like if you use that, you're not going to get any useful information out of it because all the forces are coming off of the same point. You can use the moments for the entire system, right, to solve for support reactions, but you can't use it for when we're in particle equilibrium here, right? Okay, next here's how we want to do things, right? Um, some people label it like force AB, but I just find it really annoying to write F every single time. So I just call it AB, and here's AH, right? So I'm just labeling it. I like to label it alphabetically, but you're naming each member. Um, you're naming each member the joints like alphabetically that they're connected to, right? Um, okay, here's the next thing, right? You want to assume tension, which is facing away from the particle, right? And roll with, um, sorry, I say particle, but away from the joint, and roll with this. And if you get a negative number, that means you're in compression, okay? So essentially, what I mean is you should always draw your arrows facing outwards, as to not confuse yourself with the sign convention later on. Okay, so here's how it works, right? Okay, one more thing. We need this angle, right? So I'm just going to solve the angle using rise over run. Okay. Um, so here we take 2 meters, 4 meters, right? Rises to 4. Let's get my notes up. It's like 26 or something. 26.565. This one comes up a lot, by the way, this angle. 10 half, 26.565, okay? So that's, right? Okay, so now we can take the sum of the forces up, or, sorry, vertically or horizontally. And one of these is going to result in too many unknowns. So there's actually a correct order to do this. So I'm going to take some of the moments upwards, right? So what we've done is here's the vertical component of AB, right, here. So that's sine because it's opposite, right, if we draw it like a vector. And we solve AB. AB is, don't have my calculator with me, so I'm going to have to rely on my notes here. Oh, I'm sorry guys, I didn't draw the force. I think there's one here. Yeah, sorry. Please include this. I made a mistake here. So that should be -1 here. So AB is equal to -3.354 kilonewtons in compression, right? Okay, so the reason I call it compression is whenever you get a negative number using our um, tension positive convention, it just means that your member's actually in compression, but we're just going to keep drawing the arrow facing away from the joint, even for the next part, and just write a negative magnitude. Because this way you'll never get the maths wrong, right? Um, well, I don't know. For me, like I might get the maths wrong still, but like it's less likely that you'll get the maths wrong if you do it like this, right? Okay, and then now we can find AH as well. So what we do is we replace AB with the negative magnitude, right? And when we solve for AH, we get this is 3 kilonewtons in tension, right? Cool. So that's the first joint done, and that already covers these two members. And so we're still looking for this one, and this one, right? Because we know that that one's a zero force, and we know that the rest are symmetrical, right? Oh, sorry, and this one too. So, do you want to go to joint B or do you want to go to joint H right now? Right. And you should go to joint B because if you go to joint H, you'll see that there's actually three unknown members coming off of it. So there'll be too many unknowns because of the direction of these members. So we're going to go to joint B, okay? I have the worst memory. What does it look like? All right. So with four external forces and like this one, and for support reactions, you know, you can draw the arrow um, like facing into the joint or away, depending on what it looks like, um, because it'll never flip, right? Um, so you'll never make a mistake with that, but you'll make a mistake potentially if you flip the sign convention for this constantly. But anyway, so essentially this was AB and it was negative 3.354. And now we're looking for sorry, this is B, BC, and BH, right? Okay, so um, here we want to take the sum of the forces in the x direction first, because if we take the sum of the forces in the y direction, we're going to have two unknowns, right? And just keep in mind, man, just keep in mind, the angle from before is the same, right? But yeah, oh, sorry, what am I doing? What is this? Yeah, I'm gonna quickly check the chat in case anyone said anything. Where did you get 4? Um, I'm not sure what you mean, sorry. Ashley. Sorry, that could have been with the 10. Oh, sorry, let me turn the light on. This is looking really weird. Okay, so here is, yeah, 4, I guess. Yeah, kind of rushed that part, sorry. And here was 2, so based on the geometry, we know that, it's like half the rise over the run. Okay, what else have we got? What if the bridge wasn't symmetrical? How would you find the reaction of A? Oh, um, so in that case, yeah, so I think I know what you mean. So if this wasn't here, for example, well, in that case, all the members will have a different, yeah, you can't do the symmetry thing, but I think I know what you mean. The first step of, oh, wait, I see what you mean, because these are both pin supports. Yeah, they wouldn't give you that question on this course because it's impossible to solve, yeah, with the methods that you've currently learned. Yeah, yeah. You'll get a pin and a roller usually, so it'll be simply supported. It won't be a simply supported beam, but it could be, I mean, this would be called a simply supported truss, right? Yeah. Okay, we're going to continue. Yep, so we know BC and AB. So we're just solving BH, which is -1, right? All good. So now progress check. Sorry, I know this is taking a while, but this question will be the longest one. The other two are pretty quick. So we've solved for that and that. And now we can move down to, well, actually you can go to two places. You can go to C. Um, no, there'd be no reason to go to C because you've effectively solved for these as well, and the other ones are zero force. So you basically just go to H because, well, G, you don't know the information yet. So you go to H and you solve for this member and this member now. That's exactly what we're going to do. Okay, so here's another thing. Um, Here's 2 meters and here's 2 meters, right? So we don't need to do a calc for that because that's 45, right? 1 to 1, yeah, you'll just get 45. AH, BH, CH, GH. And this is -1. This was, what was it? 3. All right, so now we're solving for CH and GH. And GH, oh sorry, if we do the sum of the forces in the vertical direction, we can ignore GH, right? And BH -1. CH gives us 1.4142 kilonewtons in tension. Like that. And now we know, just do the horizontal. GH minus AH plus CH cos 45. Worked at cos 45 is that. And AH was 3. So GH gives us 2 in tension, right? Cool. Yeah, so that pretty much does it for us. And since we specified the symmetry, then we have all the members. Do we have any questions? Okay, cool. Thank you. We'll move on to the next question. So these next two questions aren't as long, but there's a few tricks to them. Well, here we'll be doing the method of sections, right? And there's quite a few nuances with method of sections, I would say. Joints is like quite repetitive. It takes a while, but once you do like a couple of method of joint questions, they all kind of become the same. Um, Method of sections is a lot more tricks, so we'll see what that kind of plays into effect, right? So yeah, again, I kind of spilled it, but we're using method of sections because we're only interested in BC, right? Oh, sorry, BE. Do a different color. Yeah, BE, right? That's there. Um, yeah, and so here's my thought process. So the first things first is zero force members. We don't have any zero force members, right? Um, and then next, you want to think about, okay, do I want to solve my support reactions, or which support reactions do I actually need? And one way you want to answer that is, okay, where am I going to make my cut? Because from method of sections, you need to make a cut, and you're going to draw a free body diagram later of the section. Okay, so you can draw a cut anywhere that doesn't overlap like that, the same member twice. And I wouldn't recommend drawing over more than, you can do 4 members sometimes. I wouldn't do too many members pretty much because you're going to end up with too many unknowns. You're not going to be able to solve it. In general, you're aiming for about 3 members. Um, yeah, with a big asterisk. Like, I can't really tell you a rule for this, but you want to kind of cut over 3 members, um, so that you kind of get 3 unknowns or less or whatever, right? Yeah. So, and then next you want to pick a direction actually for this cut, right? So, is it going to be easier if I analyze the bottom half or the top half? It's going to be easier if I analyze the top half. And what does that mean? That means I don't need to solve the support reactions because I don't care about the support reactions because we're only going to deal with the top half of this truss, right? So I'd just like to draw the section arrows aiming upwards here. Oh man. Okay. Yeah, so I just say actually not necessary, right? Um, yeah, the supports. I mean, I just calculated them just to do it. If you want to solve for the bottom half, whatever, and then you can check. But yeah, top half I think is easier. Here's the diagram for it. Okay, so um, because I want to talk about this in the tutorial, but the next question is a method of joints question. It's not a method of sections question. I want to say that you can actually take um, the sum of the moments about a point that's not on your free body diagram, technically, right? So in this case, for B, right, if I take the moments about B, then I'm going to draw the unknown line of actions. We can actually solve for EF, right? Because 2 of these unknowns intersect at point B, and then you can actually work out EF. So you can always take a point off of the drawing, right? However, the question asks for BE, so we don't actually care about that, right? So what we have to think about is we want to take the sum of the moments. Oh, by the way, 99% of the time in method of sections, at least as the first move, you want to be taking the sum of the moments. Um, because sum of the moments is going to have some sort of way for you to cancel out all of your lines of actions except the one that you're interested in, or one of the ones that you're interested in, right? So we're interested in BE, so we want to take the sum of the moments about point D, don't we? Because then EF and BC cancel out. Okay. And in order to do that, right? So we're taking the moments about here, right? We actually have to work out this distance here. We'll call it lowercase d. Okay. And yeah, so using geometry, we can kind of figure this out. So that's a right angle triangle, right? Um, and D, okay, D is not equal to, like, it doesn't look like this, okay? It's kind of a bait, right? D is not 2, and that side there is not 1, okay? Just, like, it's based on how I drew it. I didn't draw it very well. So we're just extending this arrow and then 90 degrees off of it, right? What we're going to do is we're going to work out D. How are we going to work out D? Do it like this. Right? We know that we can form a triangle like this, right? Oh, sorry. I was using that alpha for something else. I don't think it's necessary for this question. No, it is. Wait. Wait. let me just look at my notes. Forgotten what we're doing here. Right. Okay. So let's figure out alpha. We do need it. Okay. So alpha, we have this half angle again, which was this. Okay. And then essentially, right, because of similar angles, you'll find that alpha is actually um, so I guess you can see it here. This is alpha, and this is also alpha, right? So therefore, when we're solving for D, right, it's kind of like that. Um, yeah, and we know that this distance here, do an orange, is 4 meters, right? And so we can actually derive an expression for D is that it's the hypotenuse sine alpha, which was 26.565, which is 1.789 meters, right? Yep. So now we basically now it's actually quite easy. So we just take this on the moments about D, and this external force, we can't forget about it. It's intersecting, like the line of action is intersecting the point that we're interested in, so we don't have to worry about that. But the 5 we have to take into account. So it's positive because it causes a counterclockwise motion, and it's 2 meters away. And BE, right, is going to be negative, okay? And the lever arm will be that distance that we calculated. All right, so just think about this point here. BE, this arrow is pointing this way, and it's causing this clockwise spin, so therefore it will be negative. And we can sub in D as that, and BE is 5.59 kilonewtons in tension, right? And yeah, just to clarify something I said earlier, so method of joints and method of sections, I would have the arrows pointing in tension away from the joints as a default. And then if you get a negative number, then you know that it was actually in fact in compression. Yeah, I'll check chat for questions. Nope, we're looking good. Cool. Yeah, we'll move on to our last question here. So this one's not very long. We're going to use method of joints, and I guess the main part which I've highlighted here is the note that they added. For force analysis, determination of support reactions is not needed. So in this particular problem, we don't need it because how this specific question is set up. So if you were going to do method of joints here, where would you start, right? You can start at D or you can start at B, and then work your way to either A or C. So I'll show you what I mean. So I've just redrawn the same thing, but I've labeled the support reactions as well. So I'm not going to solve for support reactions because of how the question's worded. We'll go to joint D first, which is the top left one. And then this is CD, and this is AD, right? Um, what I'm going to do, this is a bit lazy, you should probably do like the whole sum of the forces, whatever. I just say this is equal to 400 newtons in tension, and sorry, my bad. Negative 400 newtons compression, okay? So the reason for this is because if you look at how the forces balance out, this has to equal zero, right? The sum of the forces have to equal zero because we're in static particle equilibrium, right? So this has to result in a compressive force to counteract that 400 newtons, right? For AD, same thing, but in the vertical direction. So I don't even need to do any calcs for that actually. You can just look at it. Next we'll do joint B. So I've done that. Joint B set up like this, right? And same thing. BC, 200 newtons tension. These ones are in tension pretty much. And AB is 200 newtons tension as well. Right. So now we have everything except the diagonal one. Okay. So here's a kicker. Um, would you go to joint A or joint C? So if we go to joint C, right? Okay, I'll draw the CX, and this was CD, which we know, and this is BC, which we know, but the one we don't know is AC, right? Bring the arrows outwards for the truss members. CD was negative 400, right? Okay, so if we take the sum of the forces in the x direction here, we're going to end up with two unknowns. But if we take, as in the support reaction that we didn't solve for, but if we take the sum of the forces in the y direction, we can do this neat little trick. This is 45 degrees, right? Because it's 1 to 1, 2 meters, 2 meters. So we know that's 45, right? And so, yeah, now we've easily been able to solve for AC, which was negative 282.84 newtons in compression. And that's our last question for today. Cool. Um, yep. So, I'm gonna check the chat. How did you find the angle for the perpendicular distance in question two? Okay, I'll go over that in a second again. Is 200 newtons compression just 200 newtons tension? Oh, okay. Um, okay, first I'll start with the second question by Jerry here because I'll just talk about this question a bit longer. So, mm, I think the way that I do it might not be the most clear thing ever, but I think it's easier. So, and I've never been marked down for it, so I'm going to, um, yeah. So basically, what I say is whenever it's a negative number, I just put a C next to it, and whenever it's a positive number, I just put a T next to it. So I know the confusion comes from the fact that I could mean negative negative, resulting in a positive. But just the notation that I've been going off of has always been, if I put a C next to it, what I mean is that we're talking about this member has 400 magnitude in compression. Yeah. Um, yeah. I think it makes more sense in my head than the other way. Yeah. So I mean, I could just not put the C next to it. Um, but yeah, I don't know. I just feel like it works. Cool. And then how did you find the angle for the perpendicular distance in question two? So yeah, I kind of rushed this, sorry. So if we look at let's look at the original question here. We have a triangle that looks like this. Oh, well, 2, 1. We have a triangle that looks like this, right? 2, 1. So we actually know that these angles are the same, right? And so when we're finding the perpendicular distance to this, right? Um, this imaginary point, pretty much. Because we were interested in this member, BE, and the line of action extends past there. Yeah, so now we can simply pretend that this triangle looks like this, as a right angle triangle, right? And so we can solve for D as using the sine um, function. Uh, I went to write that out again, but that's kind of how I got it. It was 1 point something. Yeah. When do we decide that we need to have line extension to find D in question two? Oh, so pretty much I'm gonna draw the so every force vector or every vector always has a line of action that extends infinitely in both directions, right? Um, like this invisible line, right? It always does. And when we're taking moments, this line becomes very important because we want to find the perpendicular distance to that line in order to find the moment that it causes, right? About a certain point. And so the reason we need this arbitrary point out here is because we're interested in the force vector BE, this one, right? Um, yeah, and so to find the moment that it causes about D, uh, uppercase D, we need that legal arm, lowercase d. So yeah, this is why practicing method of sections is pretty important because every method of section question will look a little bit different. Like you might need to take this on the moments about this point off of it, like B, um, and you might need to do some other tricks. So yeah, I would prioritize practicing. Oh, like once you've nailed method of joints, after a few questions of practice, then method of sections, there's a lot more tricks to spot. Yeah. Um, I'm gonna hang around for a bit longer if there's any more questions, but everyone's welcome to leave. So thanks for your time. Yeah, no worries. See ya. Yep. All right.